we have W layer, but let me see, slideshow. From current slide. But why did I not get? Okay, let's do this in dumb way then. Let's do this. 同步显示 Okay, this should work. And it's weird, so I need to fix this. Okay, anyway, finally we get this kind of working. Yeah, so convolution property. Well, as we said before, convolution property in itself is pretty easy. So it says that you have these two signals, h of t and x of t, and if you take the convolution of them in the time domain and you do corresponding Fourier transform, then it's a multiplication of them in the frequency domain. So if y equal to convolution of h and x, then the Fourier transform of y is equal to the Fourier transform of h times multiplied with the Fourier transform of x. And the proof is pretty simple, so it's a standard thing we do all the time. And this is pretty important, so maybe let's go through this once again. So y equal to convolution of x and h, so this is just definition of convolution. And then we want to get the Fourier transform of y, so y to big Y. And so we go with the standard definition of Fourier transform. So you have everything about y here, then you integrate with HRT, so e to the minus times this e to the minus j omega t, then integrate over t. Then we do the switch of ordering of integration as always. So now we want to do integration over t first, and then look through everything which depend on t. We have h of t minus tau here that depend on t, and e to the j minus j omega t depend on t here. Okay, so just those two terms and dt. And x of tau doesn't depend on t, so it goes outside the integral. And then here we do a change of variable because we don't really know what this ht minus tau is, so we change t minus tau to t, and that sends us change t to t plus tau. So from here, this t plus tau, you get hr e to the minus j omega tau here. Then dt is sent as dt minus dt plus tau, because you are caring about t here, so tau is constant inside, and the integration area doesn't change. So this part now become integration of h of t and e to the minus j omega t dt, and that's the Fourier transform of h. So after you do the change of variable, you get big H of j omega here. The x of tau obviously is still here, and as we said, the hr plus tau here give you this e to the minus j omega tau. And now this h of j omega doesn't depend on tau, so you can put them outside. And you look at the remainder thing, you see this is just the Fourier transform of small x, so that's big X. Okay, so that's a pretty easy derivation. And as we said, this is very important, so we leave it as a last property, because this tells us a lot about the LTI system. Because now we can think, so you see this is just like how we describe LTI system in time domain, right? So you can think x as the input signal, and h is the impulse response, then y will be the output signal. This is what we say in chapter 2 about LTI system. You get the sound signal and you go through a system, the system will have impulse response, and how you calculate the output signal is you take the convolution of your your input signal and the impulse response of your LTI system. But then now we see that we can get the Fourier transform of all three of them. So kind of lose all three of them in the frequency domain, because we know the Fourier transform and the original thing in the time domain are like a pair that have the same amount of information and can transform back and forth. So you can Fourier transform everything and kind of look things in the frequency domain. Then you see the Fourier transform of y will equal to just multiplication of Fourier transform of small h and Fourier transform of x. Okay? And we also first this is a nice property because multiplication is easier than convolution. Even though we spend a lot of time talking about how to do convolution, it's still a bit annoying. You need to do the integral and care about all the sections. But now you see in the frequency domain, you have the simpler equation. You just have this multiplication here. You want to get this big Y, then you just multiply big H with big X. Okay, so that's pretty simple. And we also see this before. We have see this big H before in chapter 3. And this is actually consistent with what we had in chapter 3. Because remember, in chapter 3, we have this eigenfunction analysis. We say that for every LTI system, every complex exponential is an eigenfunction, right? So we say you put the eigenfunction into a LTI system, then you will come out with the same eigenfunction into the j omega t times the eigenvalue big H of j omega. And this multiplication big Y equal to big H times big X is saying the same thing. Because you can think about this big X, although it's a little weird because they are infinite many omega. You can think of this big X and the big Y as a coefficient to your e to the j omega t. So your function is like a linear combination of e to the j omega t times those coefficients and integrating over all the omega, right? So big X are like the coefficients to the complex exponential e to the j omega t. And this big H of j omega is still like the eigenvalue here, right? So if your input has like a big X times e to the j omega, then output will get this big H times big Y of big H times big X of e to the j omega t. And so you see that the big Y equal to this big H times big X. Okay, and but then we remember that we had another definition of this big H in chapter 3, and luckily, or as expected, the big H definition in chapter 3 is same as our big H definition here. So in this equation, we have said this big H is the Fourier transform of a small h, right? And in chapter 3, we have derived those equations for our system function, this eigenvalue big H. So we say the eigenvalue or system function big H of S, where you have this e to the st is equal to this integration h of tau e to the minus s tau. And when you restrict to purely imaginary s, so you have h of j omega. Then we have this equation big H of j omega equal to integration small h of t e to the minus j omega t dt. And but now this equation we are quite familiar, right? We just do a bit of those before. So this is just the Fourier transform of small h, right? So we see that the equation we got in chapter 3 just says that big H is the Fourier transform of small h. So that also consistent with our interpretation here. Okay. And okay, so that's a very important thing to know now. So the system function big H we had before is just the Fourier transform of the impulse response small h of t. And so we know the small h and the big H, they form a Fourier transform pair. And so that allows us to look at the system in two different ways. Very nicely, you know. The small h and the big H has this very strong Fourier pair relationship. And something in particular useful is, so in chapter 3, we didn't know how to calculate small h from big H. We know how to calculate big H from small h by doing this integral. But now we know they form Fourier transform pair, and we know how to calculate something in time domain from something in frequency domain, that is just apply the inverse Fourier transform formula. Right? So the 1 over 2 pi integration big H e to the plus j omega t dt thing. So now we know how to calculate small h from big H. You just apply the inverse Fourier transform formula. And we have seen that the eigenvalue analysis of a LTI system can be expressed as this convolution property of Fourier transform. Okay, so this is a great milestone that unifies everything we've talked about to this point, and it's very nice. No, okay. So any question about the convolution property? If not, okay, okay, and okay. So something interesting. So before we have said that, well, the convolution is commutative. So you apply two systems in different order, it's the same thing. We can also see this in a frequency domain easily. So let's say we try to apply system. We now write the block diagram in the frequency domain. So we say we apply a lattice system that's multiplied this big H1, and then apply another system that's applying this big H2. And then we are just doing multiplication, right? So if you think about doing multiplication, that is your output will be multiplied by H1 and multiplied by H2. And well, okay, so multiplied by H1 and multiplied by H2. But this multiplication is basically just multiplication of numbers. So multiplication obviously commute with each other. So that's also same as you apply the system with H2 first and apply system with H1. So we see that applying LTI systems in different orders are the same. So they commute with each other. This you can also see from our convolution property. Okay. And next thing, so we will use the convolution property to analyze a lot of LTI system. But there are some trouble here, that is, when if we want to do this convolution property, then we should guarantee that the Fourier transform of everything in our equation exists. In particular, the Fourier transform of our h of t should exist. Right? And okay, so pretty good criteria for, so we want this big H to exist, right? So pretty good criteria for that to exist is that, well, obviously, is that you want the Dirichlet condition to hold. Okay? And so there are three of them, but one of them is I guess more important. That is, you want it to be absolutely integrable. Okay? And yeah, so if our small h of t is absolutely integrable in this term, then we satisfy one of the three Dirichlet conditions, and we know that if other two Dirichlet conditions are satisfied, then our big H exists and it converges, and that's nice. And here we will just kind of hand wave and say that if this condition satisfy and the most signal, they are not going to have too many minimum, maximum, or discontinuity. So we assume that if the system is stable, so if the system has this impulse response absolutely integrable, then we think this big H exists. And also, this being absolutely integrable, if you remember in chapter 2, also means that the system is stable. Okay. So in a not very rigorous way, so we assume that our system is stable, and assume that means our big H exists, because when you have this, the integration will most likely converge. Okay. And so we are focusing on stable system where the big H will most likely exist. And for unstable system, we need a different kind of analysis. And that's where we will do Laplace transform, and that's in chapter 9. Okay, so the last part of the course. Okay, so for now, just remember your system should be stable. We'll focus on stable system, and the convolution property analysis should work because big H should exist. Okay. And okay, so now let's go through some examples. So first example is a system that we have seen before. So we have an impulse response is this unit impulse function delta of t minus t0, and I think we have written this, so you can do the convolution directly, and it's actually a bit easier than doing this. So if you do the convolution directly, you will see that this is a time delay system, and you have y of t equal to x of t minus t0. But we can also derive this by going to the frequency domain. Okay. So we have impulse responses, then we want to see what's the system function, so what's the Fourier transform of this h of t, and that's e to the minus j omega t. I think we have do this before, or you can look at it here. So you put t minus t0 here, then you will get you will make a t to t0 here, so you get e to the minus j omega t, t naught. Okay, and as we said, so the output will be big Y will equal to big H times big X. So the Fourier transform of your output signal, or your output signal in a frequency domain, will equal to this e to the minus j omega t naught times your big X of j omega. And when we Fourier transform back to small y of t, then okay, so that obviously depends on this big X, but this has a particularly nice form because when we're seeing this property, we have seen that you have a time delay in the time shift in the time domain, and then you will get this h e to the minus j omega t naught. So we know this is correspond to a time shift in the time domain. So your y of t is just a time shift of your x with this amount t naught. Okay, and yeah, so we see that this frequency domain analysis is consistent as expected, and we see that this delta function gives you a time shift to your system, and we have also seen this. You can just also do convolution, they will tell you that delta t minus t naught give you a time shift in your signal. Okay, so this is a very easy example. And next example, we have a bit singular system. But anyway, so we also see that this y of t equal to dx dt, this is also LTI. So output is just a differential of the input. And now we do the Fourier transform of both parts. Then y obviously become big Y. And then we have dx dt doing Fourier transform. We have also seen the property before, so we know that the Fourier transform of the differential is the same Fourier transform, so it become big X, but you will get the h j omega term. So you compare those two, but you see that y should equal to j big H times big X. So the corresponding big H is just this j omega. Okay. And this is a bit singular because you think about what's the small h, then you cannot quite write it because this is not absolutely integrable, but anyway, we know the big H equal to this j omega for this differential function. Okay, and yeah, actually, yeah. So also remember, if you want a small h of this, anyone want to answer what's the small h for the differential? Anyone remember? What's the small h for this differentiation function? So the small h is a very singular function. It's a unit doublet, right? So remember, small h is what happens. You put the delta function into your equation here, and so your small h of t equal to the unit doublet d delta of t dt, and it's your u1 of t. And you can see that this is a very singular function, and that corresponds to your big H being very weird when you try to integrate it. Okay. And anyway, so kind of see the Fourier transform of our unit singlet, unit doublet, and it's j omega, quite not singular. Okay. And okay, so next thing, we have the ideal low-pass filter. So we have seen this idea about filters in chapter 3. Now they make even more sense now because we'll see, we now see that we can view every LTI system as multiplying in a frequency domain as multiplying your big X with some big H. Then obviously you can set your big H as this block signal, then you will filter out your big X, right? So say your big H equal to this square signal between minus omega c to omega c is 1 here and 0 everywhere. Then you have y equal to h times x, then your y will just have your x and filter out this part. Okay? So that's pretty nice. And anyway, so now we know. Anyway, so that's the low-pass filter, and now we can calculate what's the time domain expression of this filter by doing the inverse Fourier transform. And we have done this before because this is a square wave signal, and we know is Fourier transform or inverse Fourier transform is just a sinc function, so this is sine omega ct over t. Okay? So in the time domain is the sinc function. So we know if we want to construct the ideal low-pass filter, then we need to construct this response function in the time domain. But you see that if you want to do this, then it's kind of hard, quite hard, because first it's not causal because it has this negative time component, and also it has an infinite number of oscillations here, and it's just not easy to construct. But here we will not go into too much detail about how to construct a system, so we just give a rough idea of you want to construct this. It is hard, so we want the other approximation. So maybe we'll cut off the non-causal part, and maybe we'll approximate. We'll also cut off the oscillating part, etc. And you will get a not so ideal filter, but easier to construct. Okay. And yeah. So as we said, so instead of trying to do this, we just cut off the lower part and cut off all the oscillations. So we use something that is exponential decay. Once I do exponential decay, then we've seen the Fourier transform this, then we'll get this 1 over j omega plus 1 system function. Okay. So if we instead we have time domain like this, then we have frequency domain whose absolute value is like this, so it's kind of low pace because at a low frequency it has this slight peak. But you can see that this is not ideal in many cases because you have tails on both sides, and also you have weird complex vectors. But that's more easy to construct thing. Okay. And then finally we go to this more technical part, more technical example, where we have two signals in the time domain, and so they are both in this exponential decay form, cut off exponential decay form, with a different decay rate b and a, and we want to see what's the layer convolution. So think this as you can kind of think this as this input signal, and this is our impulse response then as what's the output signal. So obviously you can do just convolution. So I've done this kind of convolution. It's to exponential decay, so you can try to set up the cases and see and do the integral. But here we know the convolution property, so we want to do it in a slightly smarter way. So we want to do this without doing integral, so we change both of those to time domain. And as we said, we have seen how this, I guess it's different, but we have seen how this kind of exponential decay function Fourier transform, it just become 1 over b plus j omega or 1 over a plus j omega. So a is this a here and b is this b here. And so we can calculate the big Y very easy. You just multiply those two together. So 1 over a plus j omega plus b, 1 over a plus j omega times b plus j omega. And but another quadrant is how you calculate small y from this thing. Okay? And I guess you can do the inverse Fourier transform formula, but the integration is pretty hard. You got these weird things. So here we have a very useful trick, or very important trick here, is that instead of this 1 over a plus j omega times b times plus j omega, we break y equal to linear combination of two terms. There is some coefficient big A over a plus j omega plus another coefficient b plus b plus j omega. Okay, it is called partial fraction expansion. And so you will need to solve for this a and b. And here we have given you a result. If you trust me, so the a and b give out, you will get this big Y like this. So this big A is 1 over b minus a, and big B is 1 over a minus b. And why we want to do this is because if you break Y equal to this form, then you remember the Fourier transform is linear. So this is a linear combination of y 1 over a plus j omega and 1 over b plus j omega. And we know the inverse Fourier transform of those two things. That's the one-sided exponential decay we had before. So we see that. So here we can do the inverse Fourier transform without doing any integration, because we know you do inverse Fourier transform, this 1 over a plus j omega, this is e to the minus at times u of t, and inverse Fourier transform of this 1 over b plus j omega is this e to the minus bt u of t. And then this ab, you are just coefficients, so we just write them down the same here. So okay, the y of t is this 1 over b minus a, e to the minus at u of t minus e to the minus bt u of t. And obviously you can also get this by doing the convolution of those two signals. Okay? Any question on this example? And yeah, so we'll see later today that we are going to do a whole bunch of this calculation. But before that, let's talk about partial fraction expansion first. So what we mean by partial fraction expansion is we are starting with this kind of term, and we want to break it into two different fractions, linear combination of different fractions. And in general, what you do is you are given, I guess, a rational polynomial. So rational polynomial, so you have some function f of x that's like some polynomial over another polynomial, and let's assume the lower part you have break down into all the factors. So you have a plus x plus a, x plus b plus x plus c, etc. And for the easy case, so when you have all the roots of the lower polynomial difference, so you have a not equal to b not equal to c, etc. Then we'll skip the proof here, but you can always write f of x as the sum of those single fractions. So instead of this f of x equal to some polynomial over this multiplication of x plus a by x plus b times x plus c, you can write it as some big A over x plus a plus some big B over x plus b plus some big C over x plus c, etc. And okay. And what's nice here is now those A, B, C are just going to be numbers. Okay, so before you have this weird poly x on the upper side, but now the A, B, C are just numbers, so it's just like 1, 2, 3, etc. But Obviously, the ABC will depend on the small a, small b, small c, and the coefficient in the polynomial up here. And so you need to calculate what are actually those ABC here. And there are kind of formula to write down for what are the ABC, obviously. But here we are being a little lazy, so because I don't think you need to memorize the formula. Yeah, so if you like the formula, you can try to look it up online. So you search partial fraction expansion, and there will be formula, but they are quite complicated to memorize. And the easiest way to do this is you can just write it as some ABC here, and so you multiply this out, you will get like XA. So if you multiply this all out with high school math, so you will get a denominator back to your x times a, x plus a times x plus b times x plus c on the lower side. Then you see you will have first term is big A times x plus b times x plus c. Then you will plus big B times x plus a times x plus c, etc. And you just solve for all the upper term will same as the polynomial you had before. Okay. So you can brute force solve for the ABC. So we will have a whole bunch of linear equation because you see that when you multiply all those things all together, then the upper part should match this polynomial. So that will be some linear functions of ABC, and you measure coefficient here, and you can solve for the ABC. Okay. So here, the thing we claim is that this is always possible, and you can always break this into this very simple form. Obviously, we are skipping a little thing here. So extra detail I skip is I didn't say a degree of polynomial here. So you only get this term if the degree is the upper degree is less than the lower degree. So you have more upper degree here, then you will get the extra term. So you basically divide those two, and you will get the extra term here, extra polynomial that's outside. But anyway, you'll probably not see those, and we assume upper degree is lower than the lower degree. And you can always write your f of x in this form. And basically, all the a you see will be what is it? And basically, how we use this is so ABC with ABC, and you want to use this with x equal to j omega. So you want to break things into two. J omega plus something, j omega plus something, j omega plus something, and with constant coefficients. Then we can do a similar thing to do the reverse Fourier transform, right? Okay. So that's a partial fraction expansion. And yeah, so we use this with x equal to j omega. And but there are tricky points. So we have this condition that we must satisfy where all the roots are different, a not equal to b not equal to c, and it turns out that when you have terms like a equal to b, so basically you have like x plus a squared, then you cannot break it into a so simple. So you will also get terms. So you have x plus a squared here, then you will also get an extra term that have something over x plus a squared. Okay. Okay. So you are left with terms like I guess I should not say 1 over x plus a squared. So like maybe a0 here, right? So we'll get terms like where am I? Here, like a0 over x plus a squared, and so we do that. So now remember x we usually take as j omega, and so then we need to do the reverse Fourier transform of 1 over x plus j omega, 1 over a plus j omega squared, right? So we have some term that look like 1 over a plus j omega, and want to know what's the Fourier transform it. And once again, we don't really want to do integral, so we use the differential property to help us. So we know the inverse Fourier transform of 1 over a plus j omega, And 1 over a plus j omega and 1 over a plus j omega square are pretty similar in that you can get this square by doing a differential derivative with respect to omega on this 1 over a plus j omega. Okay? So if we do derivative here, and then there will be some j and minus sign flying out, and if you sort it out, you will get also extra j here. Okay, and so what does this say? So we know there is a Fourier transform pair between 1 over a plus j omega and this exponential decay e to the minus at u of t, and we have seen and then we can just use the derivative property to get the Fourier transform of this 1 over a plus j omega square. So 1 over a plus j omega square, as we say, equal to this derivative of 1 over a plus j omega times extra j. And we're seeing that if you get you get a derivative here, then you will get I think it's minus jt here. So you get a minus jt on your time domain, and you multiply with this extra j, then you just get an extra t on this side. So we're using the derivative property. We've seen that your 1 over a plus j omega square is reverse Fourier transform is just t times 0 exponential decay. Okay, and obviously you can do this more time, and you will get 1 over a plus j omega to the more power, and you can get its Fourier transform like this, and basically you will get some t to the some power here. Okay. Okay. So any question about this partial fraction expansion technique? And for now it's just like this, but in the next part when we talk about the differential equation, we'll see that it's very common to use, very common when you need to use this technique, when you can use this technique to avoid actually doing the integration on your Fourier transform. What time am I? Okay, 4 minutes. Okay, we can go through this example. Let's see. Okay, and oh, maybe no. And yeah, so we can see another example on the convolution property. So we have spent quite a bit of time talking about the partial fraction expansion. So now go back to the convolution property. We have two signals, and we want to see their convolution, and they are both sinc function. So this is sine t over t, and another sine t over t with different frequency omega I and omega c. And so if you just do convolution directly, then it's pretty hard because you have those two complicated functions and you need to do the integration. That's annoying, but if you go to frequency domain, then it's very clear what this signal do. Okay? So as we see, as we know, the sinc function, you do Fourier transform and they become square wave function. And if you sort all the coefficients, then this is a square function with basically a filter for omega less than omega I. And similarly for this small h, its frequency domain is this filter for omega less than omega c. Okay, so it's a square function for less than omega c and less than omega I. Okay. And so now we think about what's the output function for this thing. Well, then in the time domain, in the frequency domain, it's very simple. So you have those two things multiplying together. Then you have a square wave multiplied by a square wave is another square wave because they are all centered around 0. And yeah, basically two filters, so you just filter for the smaller frequency threshold, right? So maybe you can do a little picture here. Okay. So you have let's say if omega I is bigger than omega, then you have a square wave that goes to plus minus omega I, and then you have another square wave that go to plus or minus omega c. Then you multiply those together, then you will just left with this smaller square wave because on the outside you get 0. And obviously if you swap the omega and omega c, then you are taking the minimum. Okay, so y is also a square wave, and then you do the inverse Fourier transform of y. Obviously you also get back to the sinc function. So you know that this y of t is just a sinc function, and with a frequency that's the smaller of those two frequencies. Okay, so I avoid doing all the integration by just going to the time domain, and I see that the multiplication of the time domain has its very simple, very simple relation, and we come back to see that our convolution of two sinc function is just another sinc function with the smaller frequency. Okay, and okay, just in time. And so let's have 10-minute break, and next class we'll talk about the multiplication property and the differential equation. Okay. Try to fix this. How do I 到底要怎么弄才可以？颜色。为什么没有 ？Display setting。为什么？诶，成功了吗这样好像有了。可以看到， Okay. Oh, okay. I think I fixed this here, and working. Yeah, and well, we say the convolution property is this property, but actually there is also multiplication property here. So, but multiplication property, as we know, is going to be very similar to convolution property because of the duality in Fourier transform. So basically, the multiplication property says that if you do multiplication on your time domain, then you will get convolution on your frequency domain. So you write out here, then it says that you have a signal that's a multiplication. So the signal R, that's the multiplication of two signals S and P. Then the Fourier transform of this R will just be the convolution of the Fourier transform of S and P. But well, here we have some normalization we need to care about. So if you check everything carefully, then you see that you need HR 1 over 2 pi here, and yeah. Yeah, and here this is the convolution between the S and P, but you have HRJ here because for the frequency domain thing we are writing HRJ here. And yeah. So that's the multiplication property, and besides being inverse of the convolution property, you can also have a bit more HR interpretation on it, because this multiplying a signal by another signal is something we actually do when we do electrical engineering. So this is something we do on radio signal actually. So not sure how many of you still listen to radio, but another way to send out signal is you do this modulation. So basically you have one signal and you multiply it by another signal, and maybe it's easier to see the picture here first. So we have a signal like this. So it's the radio signal you want to send out, has some slow frequency because it's a human text speech. And the way to do modulation is is you multiply it with a carrier signal. So see carrier signal with high frequency. And so you multiply the two signals, then you will have this high frequency signal modulated by your message signal. And you see your message will now kind of be encoded into the amplitude of your carrier signal here. So this is called amplitude modulation. So this stands for the AM for your radio signal. Okay. So you can see, yeah. Although it's a bit different because now the low point here means oh yeah. Anyway. So yeah, so this is the idea of amplitude modulation, where you multiply your message signal with a high frequency carrier signal, then the resulting signal will encode your original message as the amplitude. Okay. and so that's why this relationship also called modulation property. And so why do we want to do this modulation? So we can see what this modulation actually do when we go to the frequency domain. Okay. So we have our two signals. So the modulated signal R of t equal to our original signal S of t and the carrier signal P of t. So our carrier signal is going to be a perfect sinusoidal function, and because we are doing real actually, it depends, but For now, we think about P of t is the actual physical signal, so it's going to be a real function. So let's have a cosine omega t here. Okay? And so it's cosine omega t is a periodic function, and we can break it into two complex exponential as usual. So this is e to the plus j omega t plus e to the minus j omega t, and so when we do Fourier transform, so we look at this is the frequency domain. Those two complex exponential is going to give you two delta function. So two delta function at plus omega naught and minus omega naught. Okay. So this is the Fourier transform of your carrier signal. And now we see that with this modulation property or the multiplication property, we see that doing this amplitude modulation actually doing something very interesting in a frequency domain, that is. So you have a star signal and it has some Fourier transform, this big S in the frequency domain, look at something. And if it has a frequency much lower than your modulation frequency omega naught, then when you convolute those two things, then you will get two copy of your original signal out, right? Because you convolute a signal with delta function that just give you a shift. Although it's a frequency domain, so it's a frequency shift. So this signal convoluted with this peak here will just shift your signal to this high frequency. And your real signal convoluted with this negative omega naught peak here, then you will shift to this low frequency. Okay? So we see that this modulation can actually shift the frequency of a signal around. So that's kind of how you get a frequency band, because now if you modulate with different frequency, then your signal will get shifted to different frequency, but still have the same shape here. Okay? So you can preserve your shape of your signal, and by doing this modulation, shift them to different frequencies. Okay? It's very interesting. And okay, so now you see that you shift to different frequency. That's nice. But how do you get back to the original signal you have? So how do you actually play things out of your radio? And actually, you can just do the same operation. So I guess there are more detailed ways you can do this when you actually study the electrical engineering. But here we see a very primitive way. So you have your modulated signal R, and you just multiply with your carrier once again, the same carrier frequency P of t, and then as we know, then you are in the frequency domain. That means you are going to convolute with this these two frequency shift delta function, right? So two delta function, the omega naught and minus omega naught, and yeah, they are frequency shift, and as we know, and yeah, so they are also frequency shift, and we know what they do. So this peak is going to shift all those things by plus omega naught. So it's going to behave something at back at around 0 and something at 2 omega naught. And this peak will do the reverse thing, and it will shift things to minus omega naught. So we will shift this peak to also to 0, and this peak to the minus 2 omega naught. And there are some coefficients that so, but also when you, so there are some coefficients that I omit. So when you do this two peaks, so there are some height, and the height is actually going to become a over 2, so you kind of split it into 2. And when you do this again, you are going to split it into 1/4. So the 2 omega naught and the minus 2 omega naught things are going to have height height like 1/4, and the middle thing will have height 1/2. So you will lose some signal strength, but you can amplify it or something. And anyway, so you will see that in the middle part you will get back to your signal. So this thing has the same shape as the signal you start with, although it might lose some amplitude. And you will also get some high frequency component, and this is where filters are being useful. So now if you apply a low pass filter, then you can filter out all the high frequency component, and you get your original signal back. Okay. So this is the modulation of signal. Okay. So this is one of the application of Fourier transform analysis. Okay. Any question about amplitude modulation? Not? Then let's go to see another example. Now this is this practical example. So, but we have some signal that looks like, well, it looks like the multiplication of two sinc functions. So we have sine t times sine t over 2 then over pi t squared. And we want to see what's the Fourier transform of this signal. And as we said, this is, so we write this, we construct this like the multiplication of a two sinc function. And then we know that the Fourier transform of sinc function is a square wave function. So if the Fourier transform this is get a square wave function, the Fourier transform this get another square wave function with different width, and then we can just use the multiplication property to get the Fourier transform of those two. Fourier transform of this x, and that should be the convolution between those two square functions. And yeah, and if you write down the convolution, then it should become this weird shape. Where so you can kind of feel this as like the overlap between two square waves. So if you are in the region where the two square waves are totally overlapped, then you get this constant. And when the two square waves, so this is back to chapter 1 interpretation of the convolution. So if you square wave have the partial overlap, and when you pull them apart, you get this linear dependence on your time. On your omega. So this is now convolution omega. Okay. Yeah. So yeah, this is another thing you can do. So if your signal looks like the multiplication of two signals, then you can calculate this Fourier transform as the corresponding after the convolution of two corresponding Fourier transform. Okay. And more, I guess, communication application of this modulation or property is that we can build a frequency selective bandpass filter. Okay. Okay, so if you just want to build your frequency selective band filter with usual electrical engineering elements, then it's so all those linear elements like a resistor, amplifier, capacitor, etc. It's actually pretty hard because the central frequency of your filter will depend on property of everything, and so you need to fine tune property of everything to tune the to decide the frequency you want to select. So the frequency selective filter is like this. So you have a filter. So its Dixon function is like on this frequency axis is centered around some central frequency omega c. Okay. So you want to build this filter and you want to tune this around. That's pretty annoying, because you need to tune all the elements. But with the frequency modulation technique we had before, then we found out that we can just build a fixed frequency filter, then we can shift the spectrum around, and we can get a frequency selective filter. So the idea is like this. So you have an input signal and you want to filter a particular frequency of it. Then first you modulate it with this e to the j omega c. So you multiply. So this multiplication is multiplication entanglement. So you multiply your x over t with this e to the j omega ct. So you will shift your frequency by omega c. Then you apply your just a low pass filter. Okay, so you can control this static low pass filter. You filter it, then you shift the frequency back by multiplying e to the minus j omega ct. Okay, and this will resulting into you are actually filtering this x around the omega c that you write here. And so why does this work? So we kind of say constructing a frequency selective filter with all those linear elements are very hard because you need to tune everything. And this kind of work because we are using nonlinear elements here. So this is multiplied by e to j omega ct and multiplied by e to minus j omega ct. Those two, I guess it's still linear, but it's not time invariant. So, but anyway, so this is not LTI. Okay, so we are kind of cheating using two non-LTI elements, but this is possible with your electrical engineering, and it's very useful. Let's say in your radio, you probably want to select some frequency, and you can use this kind of thing. And let's see this in more example. And as we said, the multiplying with this e to j omega ct should give you a frequency shift, and it really shift to kind of different direction. No, wait. Okay. Anyway, yeah. So y of t equal to e to j omega t ct. Okay, yeah, and we can, well, intuitively you just see that every e to a j omega become e to a j omega plus omega c here. But you can also see this with the multiplication formula. So now we see what the big Y then is this. Oh yeah, so there is some 2 pi that cancel with each other. Anyway, so it will be like this convolution between the this will have this convolution between e to a j omega c with the Fourier transform e to a j omega c, which is actually 2 pi times this delta, but 2 pi cancel with the extra 2 pi that we had before. So we have this delta function convoluted with this frequency domain of big X. And so this is delta function of theta minus omega c. Now we have the dummy variable being theta. So this delta function integrating with X, then we'll do a frequency shift on this omega. And yeah, so you sort out the integration, and you see that it gives you a frequency shift. So this becomes x of omega minus omega c. And similarly, when you multiply with e to the minus j omega ct, then you get a minus sign, so this becomes plus sign here. Okay, and so maybe it's easier to see in picture. So you start with your x of t, and it has in some frequency domain look at something, and then you multiply with this e to a j omega ct. Then you will do time shift. So this omega minus omega ct is actually so it's a delay, and you will shift everything to the right. Yeah. So you shift everything by plus omega ct, and then you do a filter. And then you do a low pass filter here, then you are left with something like this, and then finally you shift the omega c back. So then you see that this signal is your big X, the filter around here. So it's like this signal but filter around minus omega c. So I made a little mistake. You actually filter around minus omega c instead of plus omega c. Yeah. So you see you can shift your filter around. So if you do this omega c like a different value, then you can filter out your big X at a different value. Okay? So any question about this technique? We have some extra time. Okay. So anyway, so let's do this. Yeah, so we have quite a bit of time, so we can look at this a bit more. So here is a summary of all the Fourier transform property we had. We had throughout this chapter. So for instance, the notation. So we assume we are starting with we have signal x of t is Fourier transform is big X of j omega and y of t. For Fourier transform is big Y of j omega. Then we have linearity, where if your time domain is ax plus by, then your frequency domain is also ax plus by, but with big X and big Y here. And we have the time shifting property, where your x become x minus t, x of t minus t naught. Then that will then that correspond to HR e to a minus j omega t naught vector on your frequency domain. And then we have this frequency shifting property. We just give another proof where your x of j omega becomes x of j omega minus omega naught. Then you will get HR e to a j omega naught t in your time domain. Okay, and we have this conjugation property, where you get a conjugation on your time domain. Then you will also get a conjugation on your frequency domain, and then you also get the negation on your frequency. So frequency reversal. So we get a conjugation and a frequency reversal. And then we have time reversal property, where you time reverse your signal, then your frequency reverse its Fourier transform. And from this property, you see that if x is even, then big X is also even, and x is odd, then big X is also odd. Okay, and then what's over time scaling? So you scale time to 80, then your frequency domain you will have a kind of inverse scaling. So omega become 1 over a, omega become omega 1 over a, and HR is 1 over a absolute value vector. And then the convolution property we spent quite a few time talking about today. So you have a signal in time domain that's a convolution of x of t and y of t. Then when you do the Fourier transform in the frequency domain, it's very simple form of just big X times big Y. And similarly, you have big X, you have small x times small y in the time domain. Then in the frequency domain, you have this convolution between x and y, but because of our normalization, you have HR 1 over 2 pi here. Okay, so that's a little different, but just need to remember our convention. And also we're seeing that this differential property, that if you take a derivative of your x in a time domain, then you will get HR j omega in a frequency domain. And integration, then you have this weird thing. So if your x is, you integrate your x from minus infinity to t, then it's kind of like an inverse of differentiation. So you get 1 over j omega, but you also get this HR term, this pi of x, big X over 0 times delta of omega. So we will get this weird delta function term. It's just there here. Okay. And also we can have the differentiation in the frequency domain, so it's kind of just reversing. So you have d omega of your big X, then you will get minus jt in your time domain. But we also, for reasons, we like to write this j in the frequency domain. So you have t times x of t, then you have j times t d omega in your frequency domain. And it's annoying. And we have a whole bunch of conjugation properties. Let's see. Conjugation property for real signal. So a lot of signals are real because if you consider signal corresponding to like some physical signal, most of the time they are real, right? So your current, and although sometimes it's a bit weird, but usually like you measure current and voltage, they are real. And so if your signal is real, then there are extra symmetries that you can get on your Fourier transform. So they can all be derived from this conjugation property. So if the signal is real, you know x equal to x star. Then the corresponding big X should equal to the this big X star of minus j omega. And so that means that the real part of your big X is an even function, and the imaginary part of your big X is the odd function. And similarly, if you go to polar coordinate of big X, that means the amplitude is the even function, the angle is the odd function. And then you can combine these imaginary, real imaginary, and even odd criteria with each other, so there are 4 conditions. So here we have 2 of them. So if your x of t is real and even, then big X is also real and even. And if t is real and odd, then big X will be purely imaginary and odd. Okay. And yeah, and from here we have the even odd decomposition for the real signal. So if a real signal, then you can compose it. So for any signal, you can compose it into an even part and other part. But for a real signal, you have extra symmetries where the even part is Fourier transform will be the real part of your big X, and the odd part of your X is Fourier transform will be the imaginary part of your X, big X. And finally, we have the Parseval relationship. So the energy in time domain will equal to energy in the frequency domain, but also we have this extra 1 over 2 pi here. Okay. Oh, and here we have the more general form of Parseval. So here we have the energy of 1 signal, but you can also think about the inner product of 2 signals. So you have this integration of x of t times the y star of t, then that equal to the 1 over 2 pi, the integration of big X and the big Y star. Oh, I should have j omega here, right? Sorry. It should be big Y of j omega. J omega. Okay. And okay. And oh, sorry, what happened? We have a lot of Fourier transform pair here. Let's see. Still have time. So yeah. So one thing we've seen is that if a signal is a periodic function, so it can be written as a linear combination of complex exponentials. Then the corresponding Fourier transform is a sum of whole bunch of evenly spaced delta function. So we know all those e to the j omega t will just is Fourier transform just 2 pi times delta of omega minus omega naught. So if a signal can be written as a linear combination of complex exponential, then its Fourier transform is just the same linear combination of the delta functions. Yeah, and so and then we can see then we can easily write the Fourier transform of cosine and sine. Cosine is like exponential plus exponential, so it's delta plus delta, and sine is exponential minus exponential, so it's delta minus delta. And also, if you have a constant function, then constant function can be also think of as a Fourier series, so it's just a0 equal to your constant. So the Fourier transform is just a delta function, well, also times these 2 pi. And then we think that the square root function, okay, so it's a little weird. So and we can also have a periodic square root function, and its Fourier transform will be this a little bit weird. So you have summation over different k. Summation over different k, so kind of like a sinc function summing over different k, and but it's periodic, so its Fourier coefficient is sin k over k thing, and but in a frequency domain is still this equally spaced out delta function. And then we have this very interesting function that's impulse train. So if you have equal height, equal space of delta function in a time domain, then in a frequency domain there are still impulse trains, so also equally spaced out. See. And then finally we go to the aperiodic signals. So for aperiodic signals, you have a square wave in a time domain, then you have a sinc function in the frequency domain, and then we have the sinc function in time domain with a square wave function in the frequency domain. And as we say, we have a delta function in time domain, then we have just a constant in frequency domain, and a unit state function in the time domain. Then it's really weird, 1/j omega plus pi delta in the frequency domain. And okay, so the next few things are going to be useful for the next section. So it is a thing that we would like to do for the partial fraction expansion. So, So first, we also have the time shifting in the time domain get u HR equal -j omega t naught. And then we have those complex one-sided exponential decay. So it's e to the minus at times u of t, and we have seen this function has the Fourier transform 1 over a plus j omega, and this only converge when the real part of a is bigger than 0. And we have used the differential property to derive that, so you get the differentiation on this thing, then you see that you will get the HRT on the time domain. So, and sorting all the coefficients, we have found out that when we talk about partial fraction expansion, 1 over a plus j omega squared has the inverse Fourier transform being t times e to the minus at times u of t. And saying that you can generalize this to nth power, and here is the formula. So if you have 1 over a plus j omega to the nth power, then you will also get this e to the minus at, but will multiply with t to the n minus 1 power over n minus 1 factorial. And real part of a should still be bigger than 0 for this to converge. And okay, so there are a lot of property and pairs, and they should be given to you on on test, but I think it's still a good idea to get familiar with those. Yeah. And finally, it's about time. Okay, so we actually have an extra part of this chapter that's about solving linear constant coefficient differential equation. And okay, so once again, this is the linear constant coefficient differential equation. You have a summation of different ak and y differential to the kth power, and the other side you have a summation bk and differentiation of x to the kth power. So I want to solve these equations, and we kind of already seen how to solve them in chapter 3. So in chapter 3 we say that we know if you that's why. Okay, in chapter 3 we see that so this is very annoying because in chapter 3 we see that we start with in chapter 2 we see that we have the initial rest condition. Right? If we have the initial rest condition, then the system is LTI and the COSO. And so the most important thing is, so in chapter 2 we see that if assume initial rates, then system is LTI and causal. And if the LTI system, then it has eigenfunction of is e to the j omega t. So we can just assume our x is e to the j omega t, then if assume our x is e to the j omega t, then your y will be those eigenvalue big H and times e to the j omega t. Then we can, so we just sub in x equal to this and y equal to this, then we solve big H. Then we can get a big H of our LTI system. And here we can get a similar thing, but in kind of different angle. So we just think about, because now we know Fourier transform, so we just take a Fourier transform of both parts. Right? So Fourier transform of both parts, then Fourier transform is linear, so you get the same linear combination, but this dy dt, so y become big Y, and d dt, as we know about the differential property, that just give you h. So every time you do a differentiation, you get h by j omega. So you just get j omega to a k here. And similarly, you get j omega to a k on the x side, and the x become big X. And as we know from the convolution property, so for this LTI system, in the frequency domain, we should have big Y equal to big H times big X. And we're seeing big Y here and a big X here. And so the nice thing about Fourier transform here is now this big Y has nothing to do with your summation of k, right? So all the things depend on k are here. This y term doesn't depend on k, and this x term doesn't depend on k anymore. Okay, so you can just move things around, and so we want to know what is big H here. So big H should be big Y divided by big X, and you can calculate big Y by divided by big X here. Just dividing big X here and dividing all this on AK to the other side. So we see that big Y divided by big X, which equals to big H, is just these things. So some bk and j omega to a k over some ak j omega to a k. And so yeah, so basically you can calculate all your big H from this equation directly. And so if you write down all those coefficients out, then you see that this is going to be a polynomial of omega over another polynomial. So polynomial of j omega over another polynomial of j omega. And so that will be basically the same thing you will get from doing the chapter 3 substitute. But here you have even more direct formula. Okay. And so something we need to say here. So we assume that h of j omega exists. So as we said, so for this to work, we kind of assume h is from the Fourier transform pair to small h, and that requires that you can calculate this big H. So when you do the Fourier transform from the Fourier transform integral from small h to big H, that should converge. And anyway, we'll assume the system is stable and the big H exists. And also we need to assume we are solving the system in LTI. So solving a system in initial rates. So it's LTI in the beginning. Okay. And also we are saying this here because in the later part we are going to give you the differential equation with different boundary conditions. And then yeah, so it's not initial rates anymore. But for now we are having very simple or very nice systems where we are just doing initial rates and LTI, and we can just write a system equation like this, and basically you can just read it from the equation. So let's see example here. So yeah, here is the differential equation with some coefficient. So second order differential equation on y. So d squared y dt plus 4dy dt plus 3y equal to dx dt plus 2x of t. And assuming initial rates, so it's LTI and so for system function. And system function here we can basically just write down the equation as you say. We can just read from the equation here. So it's the sum bk jk to a j omega to a k, right? So the bk are just the coefficient here, so you have this dx dt, so I give you a j omega here, and the 2x is just 2, and over all the coefficients here, so this d squared y dt squared give you j omega squared, and 4 dy dt give you 4 j omega, and you get a 3 here. So yeah, so bkh of j omega you can basically get directly. Okay? And what about we want to get something more? So this is a system function, and we say we can get small h from big H because we know how to do inverse Fourier transform now. And obviously you can brute force doing the integration of this thing with like e to j omega t, but that's very hard, and this is why we could spend a whole bunch of time talking about partial fraction expansion. So you see this is like a rational function in the form we talked about. So you have a polynomial of j omega on the upper side and a polynomial of j omega on the lower side. And so what you do is first you want to factorize the lower part. So this polynomial you want to write j omega plus something times j omega plus something, and here we have nice numbers. So this is just j omega plus 1 times j omega plus 3. And then we want to apply our partial fraction expansion to break this into something over j omega plus 1 and something over j omega plus 3. And okay, so how do I let's see, can I click this? Okay, yeah, so once again this is a partial fraction expansion. So you have a polynomial over another polynomial, and you want to write into this linear combination of polynomials. Oh, I need to get out the pointer. So polynomial over polynomial, and is this linear combination of polynomials. And as we said, so you have those ABC to solve for. There are formulas, but you can also just solve them by multiplying everything out. And let's try to go back. Can I click? No. So click. Yeah. So that's a partial fraction expansion. And so if you do the calculation here, you find it's 1 over 2 and 1 over 2. And now you can do the inverse Fourier transform because we know this j omega plus a, you do inverse Fourier transform is just e to the minus at times u of t. And you have those linear combination coefficients. Okay? Any question about this example? So yeah, so this is how you find the impulse response of this differential equation with initial race condition. Okay, and the next one we have similar. So basically the same system. So still this linear differential equation, and obviously we'll have the same system function and the same impulse response. And now we want to say if we have some input and what's the corresponding output. So we have the input, that's also this exponential decay. Exponential decay. And pick of this kind of, well, first is not too weird input, and the second is easy thing to calculate because this go to, if we know already, if you have this exponential decay, then you go to the frequency domain, then it's going to give you this rational polynomial, right? So yeah, so we know the frequency domain of this thing, then is 1 over j omega plus 1, and so the frequency domain of the output is equal to big H times big X, and big H is this rational fraction, and you times another rational fraction is still a rational fraction. So we know big Y is still this polynomial divided by polynomial, and this polynomial j omega plus 2, and the lower part we know before is j omega plus 1 times j omega plus 3, and times another j omega plus 1, now I have j omega plus 1 squared times j omega plus 3. Okay. And this is where we need to use the second page of our partial fraction expansion thing, right? So say before that, you have two roots on your lower power polynomial that are the same. Then the partial fraction expansion will get more complicated. And here is the example. So you see you have a double root around this a equal to 1 here. So what happens is you will have two terms here. So the j omega plus 3 term, you still have this just 1 over j omega plus 3 here. But for this j omega plus 1 term, because you have a square here, so you also have a square term here. So you will have a square term here, and you still have the not square term here. So you have a j omega plus 1 term and a j omega plus 1 square term here. And you have three coefficients. So a11, a12, a21, or I'm not sure why we label it this way. Oh, okay. So yeah, or you can just think ABC. But anyway, every one of them will have constant coefficient here, and you need to find a way to solve them. So once again, you can multiply everything out and equate it to this thing. And here we say those are the answer. Okay, and then we do the inverse Fourier transform. And well, this 1 over j omega plus a, we know the inverse Fourier transform is this exponential decay with e to the minus at times u of t. And this 1 over j omega plus a square we have done its inverse Fourier transform. We see that it gets extra t. Right? So we've seen this twice. So once again, let's go here. So that's why we want to do this kind of thing. So we see that this 1 over a plus j omega square thing. You do inverse Fourier transform is this t times e to the minus at u of t. This can be derived from the differential property. And we have also seen this in our cheat sheet page. Where if I do this, do you guys see? Not quite. Okay. Yeah, we have also seen this in our cheat sheet page where you can do this to n times, then you will have t to n minus 1 power divided by some factorial. Okay. And anyway, so we see that for whatever over polynomial, you can do this kind of partial fraction expansion, and we know how to do the inverse Fourier transform of all those inverse polynomials. And so you can always solve for either a system function or the output of a constant differential equation. Well, if you want to solve for the output, then your input need to be a special form to preserve your rational fraction. But you can guess that for most of your homework problem or test problem, you will preserve this form. And but you need to do co-equation carefully, so you need to calculate out all the constants correctly. And when you have multiple power, you need to remember you need to use special formula to do the inverse Fourier transform. Okay, so I think that's pretty fair timing. So as a summary, this is what we want to talk about: continuous time Fourier transform. And once again, we have the very important two Fourier transform formula here. So I think this one is the Fourier transform formula. So you integrate your XOT with e to the minus j omega t becoming the frequency domain signal, and then you can apply inverse Fourier transform by integrating with e to the j omega t with d omega, then divided by 2 pi. And also we see this convolution property is very useful because it tells us a lot about LTI system. So we see that in time domain you get convolution, in the frequency domain it's multiplication. And it's a same interpretation, or it's another way to see that complex exponential is the eigenfunction of your LTI system. And everything, just think that you can use this to solve constant differential, constant power, constant coefficient differential equation, linear differential equation. Okay, so yeah, 就这样谈。So any question or yeah, next week we'll start on chapter 5. Okay. What the fuck is